Welcome. We will continue talking about hydraulic head. Uh, so it's same objective as last time, describes the concept of hydraulic head and calculate hydraulic head from field measurements. So we will keep repeating the same thing, but with more detail. Because remember, I told you it is just one equation, but has a lot of subtlety to it. Yeah. So we will, by just repeating with more depth, we will be able to get this subtlety and get it clear. Okay, so just to revise, like what is hydraulic head? So hydraulic head, this is energy at a point expressed in meter, yeah. And by energy we mean mechanical energy, and mechanical energy has three components. It has like elevation head, yeah. Oops. It has like the elevation head, it has a pressure head, and it has like velocity head. But because groundwater velocity is small, so we can generally ignore the velocity head. And I told you flow does not depend, like flow can be from high to low elevation, from high to low pressure, but it cannot be from low to high energy. It must be from high to low energy. So flow would depend on the relative, like not on the relative value of these two, but the sum of these two, which is your total head or total mechanical energy at a point. So we've looked at this, but now in this lesson we will start to look at more details, like how to measure this one. Like this is easy, like we know where we are doing our measurement, but how to measure this one, like in the field or in general, yeah, the lab in the field. Or okay, so how to measure this pressure head? So we generally measure this pressure head using a piezometer. Yeah. So what is a piezometer? A piezometer, it could be, it's a tool. Yeah, piezometer, it's a tool for measuring like the total energy, total mechanical energy of the flowing fluid. Yeah. So it could be so see here a piezometer. So this is an example of a piezometer tube. It's a tube. So a piezometer tube, that would be a tube. Yeah. So very like it has very small diameter. It's a tube with a very small diameter. It's a very small diameter pipe with very short well screen. So you see the well screen here is very short. Yeah. Like very short well screen here. So like it's very short, like well screen. So that's like the well screen, or a slotted pipe, like, or you can have a pipe with slots, like holes in it. Yeah, here for example, or in that case it is just open from here. Yeah. Slotted pipe, it has hole in it, or it's open from here at the end, like at measure pressure at the point. So basically what I'm doing here, I know where my pipe is. Yeah. So I know like this is like my pipe here. So basically I'm measuring pressure here at this point. This is where my pipe is open. Yeah. So I have a pipe here. Yeah. My pipe, like it could have a small screen, or it could have, like in that case, it's like open here, like a pipe that's open from here. And I know where the elevation of this pipe, where this pipe is open. So that would be here, my elevation head. And then I will measure some uh, head here, and that would be my pressure head. In that, in if you are in a karst aquifer and the water is flowing at a very high velocity where this pipe is, you'll be measuring both, like pressure head and kinetic head. Yeah, like head from kinetic energy. Yeah, not only head from fluid pressure, but head also from kinetic energy. But generally, for most, like for groundwater mostly, which when it flows slowly, you'll be just measuring the pressure head, and that will give us the total head. Yeah, so I know, like I know where this pipe is. I'm measuring something here, so this is where I'm. Oops, oops. I'm measuring. Uh, it's not erasing. I don't know. Doesn't matter. I'm measuring like something here. Yeah, and that will give me, so the head would be the HP plus Z. Okay, that would be the total energy of a flowing fluid. Yeah. So basically, yeah, that would be the total energy of the flowing fluid. So the piezometer, yes, like water will rise like in direct proportional to the total fluid energy at the point. So giving the total energy at this point, water will rise. Yeah, that's how you measure it. It could be also piezometer could be also like it could be like this called like a pressure transducer. This is from like this is a famous one that's uh, commonly used in the sites called like Hopo. Okay, this is the name of the company that do this. Is called like water level logger, which is a sensor for autonomous measurement. Yeah, so it measure also pressure at a point. Yeah, so you know where you are installing it. It will measure pressure at a point. Sometimes it measure pressure. It will do like it will like some of these will also measure atmospheric pressure as well, and it will already do the calculation. It will because you know atmospheric pressure varies from one place to another, so it could do this calculation for you, and it will automatically calculate for you the is like will give you the zero gauged pressure. It will automatically give you the zero gauge pressure by subtracting the atmospheric pressure. Some sensors are like this. Some sensors you need to measure like from a nearby weather station. You need to measure the atmospheric pressure, and then you get the atmospheric pressure and you subtract it from your pressure measurement here, and that's how you get the zero gauge pressure measurement. Yeah. Okay. But so that's a piezometer, yeah. Piezometer, yeah. So it's just basically you're measuring like the water level at a point, yeah, where water will stand. It could be open from here, like it could be measuring here at this point or at this point. But another thing you also have is observation well or the standpipe that measure water level along a section. So here I'm like measuring like the pressure water level at a point, yeah, or like pressure at a point. Here I will be measuring water level at a section. So you have a section and then that would be called like an observation well or like standpipe. So water enters a pipe through like a section. Let me show you like an example here. Uh, so here, for example, yeah, what do we have here? So this is an unconfined aquifer, yeah, and this is my water table here for the unconfined aquifer. So this is my water table here, and then I put like a piezometer here. So this is the piezometer here is like stand here, and what is measuring? It will measure like my head here, which is like uh, the where the water table is, yeah, because remember water table is like a place where the head is known. So the head would be known here, the head would be known, so the head here would be like this value here. Now this is a confined aquifer. This is a potentiometric surface. Remember, this has like a potentiometric surface. So I put a piezometer here, and it's like measuring like pressure at this point. So that's like the head at this point, yeah. So that's like the pressure here at this point, HP, and that is like if that's like let's say this is my reference, and that is my Z. So that would be like, and that would be my H here, yeah. So that would be the head at this point, okay. Now, this is like if I putting a piezometer. If I'm putting like see the piezometer has like see small screen here, yeah, small screen here. If because I'm measuring like pressure here at like this point, yeah, or this point, this point, this point, this point, like anywhere along this, yeah, anywhere along this section, yeah, where I'm measuring. Now, if you have like an open screen and see this is like is like screening through like your unconfined aquifer and your confined aquifer. So basically, that could be kind of like a confusing measurement. Like you cannot use this really for modeling because I mean what you are measuring here basically will have the head value between like so you'll have like the head values that you're measuring here it would be something between like the head values that you will get from like your unconfined aquifer which should be somewhere here and the head values that you'll get from your confined aquifer which is somewhere here and then you get like some value here in between. But in that case you are it's kind of confusing because you don't know where I'm measuring my head. yeah, because the head is changing. Like the head here, like for the unconfined aquifer is here, the head for the confined aquifer is here. And if you put this, you'll get something in between. Okay, so just put this in mind. So if you are in the field, and make sure that like your people who are doing the job for you will not make this mistake. Yeah? Okay, so let's watch this video. I'm not sure. Oh, I should. Let's try to watch this video. Uh,
My sister was
let's try to watch this video. I'm not sure if YouTube will keep it or will remove it due to
at the water
copyright.
table. A key
Due to copyright, but let's try to do it, yeah. And then if YouTube remove it for copyright, then I can re-record this video again. Okay, but let's watch it and
position of
okay.
table. A key feature that gets discussed a lot when we talk about the availability of groundwater.
our learning objective is to use some simple models to define what the water table represents and take you on a short field trip to explain how the position of the water table varies relative to the land surface.
Water on the land surface may infiltrate through the soil and into the sediment and rock below. This is groundwater. This water is moving slowly downslope, eventually returning to the ocean to complete the hydrologic cycle. For more about the hydrologic cycle, see our video on porosity and permeability. In order to quantify how much groundwater is available, we need to figure out the position of a feature known as the water table.
As water infiltrates into the ground, it fills up connected spaces in sediment or rock formed by fractures or small gaps between grains known as pores. We are going to add colored water to this gravel-filled beaker to illustrate how the position of the water table is dependent upon which pore spaces are filled with water.
Where the pore spaces are full of water is known as the saturated zone. Closer to the surface, the spaces are empty or only partially filled. These earth materials are in the unsaturated zone. The top of the saturated zone is known as the water table.
Okay, let's try and find the elevation of the water table in some nearby wells. This hillside slopes down to a small pond that you can see through the trees.
There are two wells here. One is visible, the other is hidden in the shadows further up the slope. The relative positions of the wells are illustrated on this cross-section.
If we look around, we can find outcrops of bedrock not far from the wells. The bedrock here is a type of metamorphic rock.
Normally, we wouldn't think of metamorphic rock as an ideal groundwater source, as these types of rock lack interconnected pore spaces.
However, as you can see from this outcrop, these rocks contain numerous fractures providing lots of pathways for water to enter the groundwater system.
Now we're going to demonstrate how to measure the water level in wells, starting with well number 1.
Shining a flashlight down the well shows the reflection of the top of the water.
We're using a water level meter. It's essentially a measuring tape attached to a probe that will make a beeping sound when it touches the water.
The probe is carefully lowered down the well until now we measure the depth by reading the tape.
2 meters exactly. Any elevation measurements are to the edge of this PVC, so. Okay, that's good.
We'll do the same thing again for well number 2, further up the slope. This time the water level was 3.39 meters below the edge of the casing.
So let's look to see what all this means.
The two wells are about 50 meters apart, with well number 2 about 2 meters higher in elevation. From our measurements, we know the depths to the water table in each well.
Based on our interpretation, we can see that the water table is sloping gently downhill, roughly parallel to the slope of the ground surface. Groundwater is flowing downslope towards the small creek below well number 1.
The water table is the minimum depth that we would need to drill to ensure a consistent supply of groundwater. The greater the water supply, the higher the elevation of the water table.
We expect the water table to show some seasonal fluctuations and to rise during wet periods and fall during drier months.
For example, this graph illustrates how groundwater levels changed in a well in eastern North Carolina. Note that the water table was typically within a few feet of the surface, but it dropped to nearly 8 feet during October before bouncing back due to winter precipitation.
However, we can see a steady decline in the depth of the water table if groundwater is consumed more rapidly than it is replenished.
This graph illustrates groundwater levels in the course of more than 40 years for a well in western Kansas. This well is located above the High Plains Aquifer, which experiences relatively low precipitation and heavy agricultural groundwater consumption. The water table was 40 feet below the surface in the 1970s, but is around 90 feet deep today.
You can find out information about groundwater levels in wells in your state by visiting the U.S. Geological Survey's Groundwater Watch site.
We had 2 learning objectives for this lesson. How confident are you that you can complete these tasks?
Okay, so the link is here, and you can watch it later as you like. Yeah. Okay, so we learned like how to define water table and how does water table seasonally like value, like how to seasonally value. So let's do an exercise, like, so we'll do 2 exercise. We will do like, let's just start by this exercise, and so I can elaborate more on that video that we just watch it, and then we will, like, that exercise which they provided in the video, you will also solve it. Yeah. So here uh, so this is like hell, like this would be like a well, like, so you saw like the guy in the previous video, he is this is putting down this water level meters that peeps when you hit like the water level. Yeah. So that would be, you see here, this is a screen. So you see that's the well screen. You see here, that is like, let's say, where is this? So this is depth to water. This is like your land surfaces here. Oops. Nice one. And see, like your land surface is somewhere here. So the guy is standing on the top of the land, and you see here casing stick up. So make sure when you do this measurement, make sure you subtract this casing stick up. Yeah. And this is your datum. So your datum is here. So that's where you measure your Z. Yeah. Okay. So let's try to do this. So that's your datum. This is like the casing. You do some grouting here. You do some bentonite seal here to prevent like contamination. That's like your elevation is here. That's where you measure like your elevation. So land surface elevation. And casing stick up or depth. So like that's like where your land surface elevation, but on the top of this land surface elevation, you have this casing stick up also. Yeah. And then you have here the depth to the water. Like, so you put this like water level meter, and it will make peep peep when it reaches here. Yeah. So basically, when you go to the field, that's the information that you will be getting. Yeah. Like, what is the land surface elevation from my datum. So that's like my datum, that's the land surface elevation from my datum. So in that previous examples, they have two wells, so you get like this datum could be like sea level, for example, yeah, or whichever datum you are using, yeah. So that would be like my land surface elevation from the datum, and this information will generally be provided with the well, right? With this well, it will be provided with it, yeah. And then casing stick up depth. So the casing stick up depth, that's basically, so here is the land surface elevation. Yeah, this is just the land surface elevation, and the casing stick up would be like you measure this section here. Yeah, you measure from here to here. So you get this, and you got like different measurement for this guy. Yeah. So one of it is like zero point 0.3 meter, -4 inch, 1.25 feet. Yeah. So we need to convert this like to make it consistent. This is a meter, so we need to get this in meter. And then you put like your water level meter, and then that one it peeped at 21.6, 12.5, 26.1. And then I'm telling you like what is the head here. So the head here would be basically the elevation, yeah, from your data, plus the casing stick up minus the depth of the water, yeah. So that's basically because like you will like put this here and you will read the number from here. Like you put the tab here and then you read the number from here. So it is the elevation plus the casing stick up minus the depth of the water. So try to do this, try to solve it, make sure to convert this, and then get back to the video. Okay. Okay, so welcome back. So what is so you'll get like if you did it correctly, you should get some values that looks like this. Yeah, that will be the head. So here this well has the highest head. This is medium, and this is the lowest head, which would indicate the flow would be from like I don't know where these two are, but like toward this one. Yeah. What indicated like what you have here a negative casing. What does this indicate? Like what does a negative casing mean? Negative casing stick up depth is like negative. What does this mean? This basically indicate like this negative. This indicates that the casing measurement indicates that the casing is below the land surface. Like the casing, like here, like this is like your casing here is like below the land surface. So that is what would be the negative. And let me show you like, so negative measurement indicates that the casing is below the land surface. So here is an example. Like you see, here is your casing. So that's like your land surface is somewhere here. And like your casing is somewhere here below the land surface. Yeah. So that is a negative casing. Yeah. So that's like your land surfaces here. That's like, and sometimes we do this, we cover it because of vandalism. Yeah. And for more additional resources, like if you want to know how to do this accurately in the field, and or or how USGS, because USGS, as you saw in the videos, they have national data for these hydraulic head measurements. Yeah. So for Florida everywhere, yeah. So if you want to know how the USGS do it and the rigorous method for doing this in the field, please watch like these videos. So if you go to this link, you will find like these series of videos, and they are short videos, and then they will show you this in detail. So if you ever will go do this in the field, make sure to watch these video before you go to the field. Yeah, make sure to do this. That's very important to watch this video before you go to the field. Okay, but here let's do an example. Let's do another example. That's basically the example in the video. So here you find like the casing, and the casing has some stick up here. So you need to measure this and subtract it. And then you find like you have, this is like your water level meter. We have one here at FGCU from, I should have showed you the one we have here at FGCU. I think I showed it to you before in another video. Okay. In the video about the hydraulic gradient, I think I showed you the one we have. But that's good. Like, so now you're seeing two of them. Yeah. That's from a different company. So you basically go here, you put this down, and it will peep once it hits the water. And then you have a tape here. You read the measurements, like whatever you're from here. And then so water level is measuring tape attached to the prop that makes beeping sound when it do. And then what is this? So this I was like once doing this in the field in a dairy farm in Ireland, and it's a dairy farm, so it has cows, and this is happy cow that make a very good butter and cheese also. And I was like doing these measurement in the field, and after I was done with my measurement, and I just found a big head just looking into this borehole with me. And I was like kind of scared. What is this big head that's looking inside this borehole with me? And it turned out to be this cow. And I got to learn an interesting fact that cow are very curious creature. So they wanted to know what's down in this hole and what am I doing there. So I was scared by the cow, so I said, okay, you scare me, I'll take your picture. And now it's the cow here is posing for the picture. So yeah, like if you are in the field, yeah, make sure that you have like you just have a safe safe settings around you. Cows are okay, cows are not a problem, but make sure that the field, for example, will not have a pole. Yeah, pool. Yeah, I cannot pronounce it. Sorry, pole. Yeah, does not have this guy. That's dangerous. Okay, they look scary also, not just dangerous. Yeah. But anyway, so here this is the problem which we saw in the previous video. So let's try to solve this problem together. So that's the ones that I showed you in this video by the University of North Carolina. I guess it was the University of North Carolina. I know. Find the depth of the water table in each well and flow direction. Yeah, so basically I'm telling you here uh, what is the depth of water, like what's the depth of the water table. So I want to find like this value here, like the head here and the head value here. And assuming a horizontal flow, so there is no like there's no up gradient or like down gradient like this. The flow is just like horizontal, yeah, assuming horizontal flow. So that makes find the hydraulic gradient between the two wells. So I want you to find the hydraulic gradient. Remember hydraulic gradient, that's like delta H over delta X. So to find the hydraulic gradient, I need to find like head 2, yeah, and head 1. And then I need to find delta X, like the distance between, that's like delta X here. And that's like, so hydraulic gradient, that would be head 2 minus head 1 divided by delta x. And in that case, it would be negative, yeah, because head 2 is smaller than head 1, yeah. Okay, okay, so here is the information that you are given. Uh, Here is the information that you are giving. The elevation here is 100, and this is here is 102. Yeah, and the depth to the water is 2, and the depth to the water is 3.14. Yeah, and the depth to the water is 3.14. So basically, like if you subtracted this guy from this guy, so that is uh, that would be like this one here, and that will give you, oops, so like you subtract this one from this one, and that will give you like the water table here. You subtract this one from this one, and that will give you like the water table here. Okay. Uh, so basically that is like, so you measure this here, so the water table, like the head here, head 2 is 98, and the head 1 would be like this value here. Okay, and that's the flow direction. So the what you call it, the head gradient would be delta H over delta X divided by the distance. So the distance here is giving as 100 meter. So you got, as you expected, you got like this negative value here. Okay. Well, let's do, so this exercise is mainly horizontal groundwater flow. Yeah, I told you this is like the flow is horizontal, but if you have vertical groundwater flow, then you can have like an upward flow like this or a downward flow, like not horizontal flow. And so let's look at this example. So that's like a third example which we will be doing. Vertical groundwater flow, the flowing field. So in the field, like is a nested piezometer will install side by side at a single site. So a nested piezometer, these are like yeah, small pipes here or tubes or whatever, and they could be all installed like in the same casing at a different depths. So here, like one is installed like here, one it is installed like, so oops, my drawing is not good. So let's say that's your casing here, yeah, and then you have one tube here at like this depth, for example, like another tube here at this depth, for example, and a third tube here at this depth, for example, and that's like the same casing. So that is the same casing. Okay. And then, so at well, like let's call, for example, like, let's see, depth of the piezometer depth. So like well C is a piezometer, well A, that like this call, like this is the piezometer depth is the deepest one, that's A. Well, B, that's like would be B, and that would be C, for example. Yeah. That would be the piezometer depth. Yeah. So that's called like a nested piezometer. We're taking for a nest of piezometer or nested piezometer. So you have like surface elevation. So that's like your surface elevation from mean sea level. Yeah. Piezometer depth, that's where like the piezometer is, like the piezometer depth, and depth to the water level, like so that's where the water was measured. Yeah. So let's look at this. Let's plot this. So I'm asking you, okay, assuming horizontal distance between this is negligible. So they are all installed in the same place. Yeah. Calculate the following. Yeah. Hydraulic head, pressure head, vertical gradient between A, B, and C, like the vertical gradient, like the vertical gradient, not the horizontal gradient. So the vertical gradient would mean that you need to get the distance from here to here, for example, or the distance from here to here. Yeah, that would be the vertical gradient. Horizontal gradient would be like to get the distance from here to here. Vertical gradient would be, oops, would be to get the distance from here to here. That would be the vertical gradient. Yeah, my drawing is very bad. I will show it to you in the next one. Okay. Let me clear the screen. Okay, it doesn't matter. Okay, and vertical hydraulic gradient between them. So let's plot them. Like I think if we plotted them, things will be clear. So let's plot the information that we have. Yeah. So that's the reference. That's my where I like my mean sea level where Z is 0. So that's like my reference where Z is 0. And here, let's look at these one by one. So this is the depth to the water level. So here I put my water level meter, and then I will measure like 27. Yeah. So that would be the 27 here. Piezometer depth, this is where the piezometer is installed, like 150. Yeah. And then surface elevation, that would be above mean sea level. That would be the surface here where of course you need to like to subtract like this head casing up, but I'm not in the previous example also the head casing up was also subtracted already. Yeah, but so like you need to subtract this one. Yeah, but I'm just showing this here for illustration. Yeah. So that is the depth to the surface, like after, yeah, like when you do your measurement after you subtract this. Yeah. But anyway, so now so that's like basically how you do it. So like, can you tell me here? Can you tell me here where is the elevation head and where is that's a good exercise. So you get this data from the field and now you need to interpret it. So where is the elevation head? Where is the pressure head? And where is the total head? So for well A. So for well A, obviously, this part that would be your elevation head. And this part that would be your pressure head. And like from here to here, that would be your total head. Yeah. So that is basically how you do this. Yeah. Okay. So that's head one or head A. Similarly, that would be like head B. And similarly, that would be like head C. So now I can easily calculate this. Yeah. Now I can easily calculate like the head at A, head at B, and head at C. So use this number and please calculate this. And then come back. So calculate like head A, head B, and head C, giving like this information that you have here in the table. Okay, now you calculated head A, and head B, and you calculated, you know you can calculate each one, like the head pressure, this one, you can also calculate like this one and this one, just giving this value you have here, yeah? So try to calculate like this one, like giving the values that you have here. And then now let me ask you, now it's not only asking you to find the head, but it's asking you to find also the vertical gradient, like this, like delta H over delta ZKZ. So basically, if you did this, like, so you'll find like head value here. Obviously, the head here would be larger than H. A would be like this, HB. This is HC. So obviously HA would be larger than HP. What does this mean? This means that you will have like an upward gradient. Okay, so you how to do this? Like how to find like the gradient, like this upward gradient. So from A to B, so that would be HB, oops, HB, like whatever value you'll get from here minus HA, whatever value you'll get from here over the distance. So that's the distance that would be here. That would be Z delta Z between A and B, like that distance here, or delta Z between A and B. Okay, so that's how you solve. So try to solve it and try to do this calculation. I think you have something like this in your homework or in your exam. I don't remember, somewhere. Yeah. But you'll get this like, so this is a good exercise that will help you to prepare for your homework and for your exam. Okay, so again, I told you this is the head at A, this is the pressure head at A, this is the elevation head at A, and here, this is just what I was showing you. This is the distance between A and B, which is in that case would be, you can calculate it from this number like 50, okay? So if you did this, this is again, if you did this, you should get something like this. The hydraulic head values that I got for this one is this. The pressure head values that I got for this one is this. And the vertical gradients that I got for this one is this. From A to B, you got a negative value upward from A to B. We expecting this because the head here is higher than head here. From C to B, from between B and C, so flow downward. Again, here's a flow. Here would be like, so here you see like this point is here, this point is here. So again, this is like a higher head here. So you'll get the distance would between B here. So you'll get like a downward gradient. Yeah. So here you have like an upward gradient towards this one, and you have a downward gradient from here to here. Okay, so let's like in real life, how will this look like? So would it be like, okay, so this is my head measurement here. Would it be like this one? Or would it be like this one? So this one here, you have like a lake, yeah, or like a river or a stream or whatever that's fed by groundwater. So we call this like a gaining stream. Here we have a lake or stream or whatever that is like losing to groundwater. We call this like a losing stream. Uh, uh, Here you have like a losing stream, but below it you have horizontal groundwater flow. And this case is where you will have like it's a gaining stream on one side and it's a losing stream on one side, but it's also gaining a stream like so it's like from one side it's a gaining stream, from the other side it's a losing stream and a gaining stream, like in different section depending on the head. So which like that's my question to you, like so that previous examples that you just show, the previous example we were, yes, like if we were like spread like these wells, like not making like nested piezometer all in one casing, but spread them, like we took like three different measurements, yeah, and these are the three different measurements that we are taking. Which will be which case you will get, like so for example, like you went to a lake, yeah, and at this lake, you did some measurement. You did a measurement here, you did a measurement here, you did a measurement here. Which, how would you interpret this? Would you interpret this as this case? Would you interpret this as this case? Would you interpret this as this case? Or you will interpret this as this case? Yeah. That would be your thing here. So let's look at from here to here. So from here to here, like this is where I'm measuring my head here, and this is where I'm measuring my head here. Yeah. So I'm measuring my head here. I'm measuring my head here. So what does this tell me? This tell me I have a down gradient. Yeah. Here I'm measuring my head here, and I'm measuring my tail here. This is telling me I'm having like this down gradient, like water is flowing from here to here. So is this case? I don't think so. Yeah. How about here? Here I have this here and I have this here. Like sorry, I have this is the heads that I'm measuring here. This is the heads that I'm measuring here. Here is higher than here, which means I have flow in this like from here to here. And this is the heads that I'm measuring here. This is the heads that I'm measuring here, which means I have flow from here to here. Is this the case? Well, uh, I don't think so. Yeah. Uh, how about here? Yeah, like you look here, this is the heads that I'm measuring here. The heads that I'm measuring here at this point, at this point, at this point. This means water is flowing from here to here and flowing from here to here. Does it look so? I don't think so. Yeah. How about here? Like you're measuring this here, we are measuring this here, we are measuring this here. So water is flowing from here to here, maybe, yeah? And water is flowing from here to here. That is also maybe, yeah? So uh, it's either like you see here, like it's either you are getting like this case, it's either this case or this case, yeah? This would be one of them, yeah? I don't know, like here, I don't really know like which one. Like I know like here from this one, I don't know whether it is this one or is this one because it could be also this one, yeah. Because here, like because like here, it's just showing you that from here to here is going upward. But actually, no. Actually, it should be like see, it's tricky. It's not easy, yeah. It's not easy to interpret these things. That's why you go make these measurements in the field. That's why you're taking this course to have this knowledge. So let's look at this more carefully, yeah. And maybe the answer would be we cannot decide. We need more measurement, yeah. So you get like this here, you get this here. So this means that my water is like I have this here. So you will draw some like so how to do this, like you do some equipotential line maybe here, and then you draw like uh, maybe yes, like it would be the flow direction would be something like this, yeah. P should be perpendicular, yeah, it should be something like this. So it is most probably it will be this one, yeah. That's because that's where you can get like this type of flow direction. But it could be also this one. You might, to confirm, you might put like another like one here at a different depth, and then you'll be able to see like this gradient. Yeah. and how like water is moving vertically. Okay. So in this case, I will go for maybe A. Yeah. In this case, I will go for A. But if you have a different opinion, just let me know in your exit ticket. Okay. Uh, Okay, so this is another one. I want you, I'm not going to do this one. I want you to do it, and then after you do it, to check the answers. The only the difference between this one, I'm telling you, like whether you have like a vertical flow or horizontal flow, and you can decide this based on like just read this, yes, and this is like depth of groundwater, and then like you find this difference. So if this difference is like positive or negative and above like a certain number, then it should be like just read it, yeah, then it should be upward or downward gradient. If not, then it should be like a horizontal flow. Okay, because these are nested piezometer. Yeah, so a vertical component determine field by measuring depth of water adjacent piezometer. So these are nested piezometer. Like I have three piezometer on the same thing. So if the gradient between like three piezometer at the same point, so if the gradient between these three piezometer at the same point is large, let me remember. Let me show you like an example for this one. So here we go. Yeah. So that's like a case like this, yeah. So this is like a nested piezometer. So they are at the same location, like at the same location, at the same casing, yeah. So at the same location and at the same casing, I measure my head here, and I measured my head here, and then I found my head here is larger than my head here. This means that I have a down gradient, yeah. Now we are getting back to this, yeah. Here is another nested piezometer, yeah. So this is another nested piezometer. So I measure my at this location and at this location, I measure my head here and I measure my head here. Uh, so and I found my head here is larger than my head here, which means that like this is going upward because the head, like see, from this point is higher than the head at this point. This means that water will go from this point to this point. At this point, the head here is higher than the head here, means that water will move from here to here. So that's basically in this exercise, I'm giving you this number and I want you to say whether this is like a upward or downward, but there is a trick to it. That's not it. The trick to it is that it is uncertain. Like how you can measure this in the field, it has like this error tolerance, yeah? So that's like the error tolerance. So basically, if you find the difference in head is like less than this value, then you cannot decide because like your instruments, your measurement instrument, your tube or your piezometer does not does not give you the accuracy you need to make a decision. So please carefully read this, answer it, and then check the answer at the end. That's a good exercise for you. And I think you have something like this similar in the exam or in the homework. I don't remember. Yeah. But anyway, so if you did this, then your final answer should look something like this. Okay. So I think that's all for this lesson, and I will see you in the next lesson.